Dear students, I start with lecture 22 of Math 305. In the previous lecture, I introduced very important definition of number theory, and that is Euler's phi function. In this function, we define phi n as a number of positive integers not exceeding n and that are relatively prime to n. So this definition will ask you in so many times. In university papers also, you should learn this. I have already given you the definition in the SYBSC when I taught you about abstract algebra. And there was a Fermat theorem also. But now we start with the advanced applications of this one, and let's start. 12. Result. Prove that n is prime. Double implies phi of n equal to n minus 1. Proof. Suppose n is prime. Then every positive integer less than n is relatively prime to n, and therefore phi of n is exactly n minus 1. So this proof is very obvious. Second part, if phi n equal to n minus 1, we claim n is prime. If n is composite number, then n has a divisor d such that 1 is less than d less than n, and therefore phi of n is less than or equal to n minus 2. If it has at least one divisor, then also phi n have at the most n minus 2 value, but the value of phi n is n minus 1, and therefore phi of n is n minus 1. Therefore our supposition is wrong. Therefore n is prime, and therefore theorem. If P is a prime and K greater than 0, then phi of P raised to K raised to K minus 1, or this is equal to this we want to prove. You should always remember the definition of Euler function, Euler phi function. What is definition? Euler phi function is the total number of elements, integers which are less than or equal to n and relatively prime to n. You should keep all the time in mind. Otherwise, what we will prove if you have no idea about the Euler function? So, try to remember it. So, if 1 less than or equal to n, less than or equal to p raised to k, then n in p raised to k equal to 1. N does not divide p raised to k, or p does not divide either. This GCD is what? If also p, 2p, 3p up to p of k minus 1 time p, 1 time, 2 time, 3 time up to p raised to k minus 1. This is first, this is second, this is p raised to k minus 1. These are the only numbers which are divisible by p, because p is a prime number. Therefore, we have to exceed this number from p raised to k. Are the only integers which are divisible by p. These are p raised to k minus. Means it is 1, 2, 3. How much? P raised to k minus. Like this. Therefore, means these are the integers which are not relatively prime to p raised to k. Therefore, p raised to k minus p raised to k minus 1 integers which are relatively prime to p raised to k, and therefore phi of p raised to k, and therefore this proves. In 14, we have some example. Pi of 9 is pi of 3 square. Means this is equal to 3 square minus 3 means 9 minus 6. 9 minus 3 means the answer is 6. Means there are 6 numbers which are relatively bright to 9. And by direct calculation, one, two, not 3, 4, 5, not 6, 7 and 8. These are 6. Another example, that is pi of 16. This is pi of 2 raised to 4. And therefore, as per the this theorem, it is 2 raised to 4 minus 2 cube. So it is 16 minus 8. And therefore, these are 8. And by direct calculation, one not 2, 3, 4 not 5, 6 not 7, 8 not 9, 10 not 11, 12 not 13, 14 not 15. 1, 2, 3, 4, 5, 6, 7, 8. So this is by direct calculation. These are the numbers which are relatively prime to 16, means they are 8 in numbers. Given integers ABC, GCD of A and BC equal to 1, if and only GCD of AB equal to 1 and GCD of AC equal to 1. So obviously this proof is in 2 parts. So we start with part 1. Suppose GCD of A and BC equal to 1. Let D equal to GCD of A and B. Therefore, D divides A and D divides B. As it is GCD, it must be, and therefore as D divides B, D divides BC. Now D divides BC means D divides A and D divides BC means GCD of A and BC greater than or equal to D, but A and BC equal to 1. And obviously by default this value must be greater than or equal to 1. And therefore D equal to 1 means GCD of AB equal to 1. Similarly, GCD of A and C equal to 1. So we start with the converse. here GCD of AB equal to 1 and GCD of AC equal to 1. If GCD of, what we want to prove? We want to prove that GCD of A and BC equal to 1. Suppose this GCD is B1 and it is greater than 1. Therefore, there must be prime P where P divides B1, therefore P divides A, P divides BC. But by this part, P divides B or P divides C. Now if P divides A and P divides B, therefore P divides GCD of A and B greater than or equal to P. But this GCD is 1. P is prime. There is 1 is not prime. Prime starts from 2. And therefore, this GCD is greater than 1 is false. We have the same result when we choose P divides A and P divides C. At that time, GCD of A and C greater than or equal to P, but this value is equal to 1. Again we get the absurd result, and due to that I can say that this is false. So this is very important result which we use to prove phi is multiplicative. Dear students, in this theorem, it is must for university exam. The function phi is multiplicative function, that is phi of mn is phi f phi n. This is definition of multiplicative function. And we want to prove this. Actually, I start this theorem just explanation for you to hear, but I will prove it in the next lecture. But I will give you the brief information with the starting of this proof. So here, we want to prove that phi of mn equal to phi of n and phi of n. The one thing is that which was not mentioned there, but it is there, and GCD of m and n equal to 1, and this we want to prove. I say this as equation number 1. If m and n or n equal to 1, if m equal to 1 or n equal to 1, then as I of 1 equal to 1, and phi of 1 equal to 1 implies 1 is 2. So we have to consider the case in which m and n both are greater than 1, and then we prove this theorem, but in next lecture. For this lecture I stop here. Thank you very much.